now actually going to be moving away from our own solar system. We got to talk about a bunch of different things in our own solar system. We're now going to be moving outside of our solar system to extrasolar planets. And the first talk will be by Sarah Ballard from University of Florida, who will be talking just a little bit about how can we know anything about exoplanets and their atmospheres at all. So Sarah, please take it away.
Thank you so much, Paul. And I'm also honored to be the second in a series of 3 Sarahs giving talks. So I aim for this talk to sort of give some connective tissue between the talks that we saw earlier this morning about the solar system and the talks that will follow subsequently about the interpretation of exoplanet atmospheres. I tasked myself with a job that's twofold, and it's suggested by the title of my talk. So one of those 2 purposes related to kind of the cutting edge is how technologically we're abutting what's possible with exoplanet atmospheres, but a ceiling is also established right now, corresponding to our understanding of stellar physics. I'll explain why that should matter so much. And also because this is suggestive, the cutting edge, it's actually with the limb of planets, the limb of worlds that constitute our best chance for detecting the molecules and atoms that constitute exoplanet atmospheres, at least probably for the next decade or so. And I mean that to be suggestive from this image, which is actually of Titan. So we heard so much about this incredible world from Zibby in the last session. This is actually an image of Titan backlit by the sun. And I like to start close to the solar system for understanding exoplanets generally. So this is an image that was actually gathered from the Japanese Himawari spacecraft, a weather spacecraft. This is actually in very familiar and recognizable units of wavelength, namely the visible. And yet you can see that limb of the atmosphere. It's very suggestive here. It's sort of hazy. We can see some blue from the Rayleigh scattering in the atmosphere. I'm now going to show you what it looks like at a different wavelength. So in the infrared, I'll sort of go back and forth. You can see that the size of Earth's atmosphere, using the moon as sort of a convenient backdrop here, changes. So going between 8.6 microns in the infrared to 9.6, you can see that the relative size of our atmosphere is shifting, depending upon which wavelength we're looking at. This is the singular idea which undergirds our hopes for detecting exoplanet atmospheres, this exact same idea. So I'm showing here the axes, which you will see in the subsequent set of talks, which are the ones that we will depend upon in order to extract these measurements. So this is as a function of wavelength on the x-axis. Visible light is over here, shorter than 1 micron. And then on the y-axis here is the relative size of the atmosphere, sort of perceived size of the atmosphere. Now, from the data that I just showed you, gathered from a spacecraft orbiting planet Earth, we have 3 pieces of wavelength information. Namely, we have this observation in the visible, we have one observation at 8.6 microns, and we have an observation at 9.6 microns. So actually filling out this graph is something we can do in real time. So here we have this axis for the so-called transmission spectrum. In the visible, there's some fiducial apparent size to the atmosphere. Moving to 8.6 microns, the atmosphere appears to be smaller. Then going to 9.6 microns, fractionally, the atmosphere appears bigger than it did in the visible. So even if one only had these 3 measurements, one could start to make inferences then about what the atmosphere must be constituted of in order to have these particular properties associated with absorption. So this is the actual real model transmission spectrum of Earth. This is data generated from Ty Robinson at the University of Arizona. So you can see the reason why Earth's atmosphere looks so much bigger at 9.6 microns is because of ozone in Earth's atmosphere. So one can imagine by steadily gathering a set of observations, namely looking at the size of a planet's silhouette at a number of different wavelengths, you could then reverse engineer based on the apparent size of those transit depths or occultation depths, what constituent particles must be present in the atmosphere. So that's the idea in theory. How large is this signal quantitatively? And I think a really good example of how to do that, if you haven't thought actually to scale about planets in a while, for those in the audience who specialize in other areas, this is showing a globe. Now, Earth's atmosphere is actually shown, held here by this helpful volunteer in the form of a piece of packing tape over the surface of the planet. So Earth's atmosphere is actually extremely tightly bound to the planet. This is corresponding to roughly 15 kilometers, in fact. So you can actually see to scale how that would look here. Right? So when we talk about Earth's atmosphere, this is an extremely, extremely thin ring when perceived in silhouette. Let's talk about how small. So it's the characterization of a planetary atmosphere by backlighting, which really is this necessary concept, which probably will support claims of the detection of biomolecules at least for the next decade. And I'm referring to transmission spectroscopy here, namely the backlighting of an exoplanet, by which you can then see that illuminated ring from behind and then make inferences about the relative opaqueness of that ring. Now, the example that I showed you with Himawari used the moon. As the backlight. With exoplanets, we actually have a very convenient backlight for transiting exoplanets, which is their host star. So in this animation from the European Southern Observatory, you can see that even though we don't have this beautiful resolved picture of an actual planet in front of a star, we're able to measure, based on how that star's brightness changes when the planet's in front of it, what the relative size of that planet must be based on the size of its shadow. Now, I like this illustration not only to sort of illustrate, the notion of transits, but because this image of a star that's used in that animation was also very heterogeneous. It's extremely suggestive of the ways in which stars present like an imperfect backdrop. More on that in short order. So let's talk about the relative size of this signal. So I'm showing here a sun-like star. Let's imagine that we're receiving 10 million photons from it. To use an analogy which Jan used a couple slides ago, let's consider a pint glass. And this pint glass is full of grains of sand. There are roughly 10 million grains of sand that would fit inside of a pint glass. So to put it to scale with human ability to resolve changes in brightness, depends on whether you're talking about rods or cones. I had to Google it recently. Our ability to discern differences in intensity is a difference between 1% and maybe 10%. So we're talking about perhaps a teaspoon of sand out of the total pint is roughly what humans are able to discern, maybe a few teaspoons. And indeed, that constituted the first detection of a planet using this method, namely having a planet blocking the face of the star. But that was a Jupiter that blocks a teaspoon. In front of a sun-like star, a star like the sun, we're talking about 840 photons or particles of light being blocked out of every 10 million. So, a solid pinch in this recipe. Yet, we're not just talking about the planet's silhouette entire. We're having a discussion about the ring, the tiny ring of atmosphere, the 15-kilometer in excess on either side of that planetary shadow, which would potentially appear different depending on what color we're observing it at. So the sensitivity which would be required to tell the difference between an Earth-sized thing in transit and an Earth-sized thing plus 15-kilometer ring all around it is something like 4 in 10 million, or we would say 4 parts per billion. So that's 4 grains of sand. What we would need to be able to detect the difference between a pint glass containing just the starlight and one containing the starlight minus the planet is the planet's atmosphere is 4 grains of sand. Very, very hard experiment to design and yet tractable from humans. There's a reason why they haven't been mentioned yet, but in the exoplanet community, people don't talk about sun-like stars as uniformly as they once did. In fact, our attention has really turned to small stars. The reason for that is more complicated and interesting than I have time to get into today. But one thing I'll emphasize is that it is much easier to characterize planetary atmospheres around small stars, so-called M dwarfs, half the mass of the sun and smaller. And that's because not only does the size of the planet's shadow get fractionally bigger, the size of that planet's atmosphere gets fractionally bigger. So this is roughly 10 times the size of the signal for a world of the exact same size. If we add the atmosphere on top fractionally, we get that same boost. So now 40 grains of sand, right? Which is like not as seemingly intractable, and indeed. It was this sort of sensitivity that constituted the design of the James Webb Space Telescope. If you haven't heard about the James Webb Space Telescope studies of exoplanets, you'll hear more about them in very short order. So this figure actually predated the launch of James Webb and showed why it was designed with the precision that it was. So this like 4 parts per million argument, the sensitivity required to distinguish between a bare rock, a bare Earth-sized rock, and one with an atmosphere on top of it, particularly an atmosphere which might be outgassed, have a higher mean molecular weight, which is to say no hydrogen in it, is roughly 4 parts per million. And you can see on the y-axis there how 4 parts per million would be sufficient, hopefully, to distinguish between a completely flat line and a planet whose relative size changes because there's water, for example, or CO2 in that atmosphere. Now, you can sort of see on the bottom a bunch of stats related to this simulation, including that it would take 28 hours, namely, that you would need to stack 10 transits together in order to see this. You get a real benefit also if the planet is larger. Of course, that's going to be the case. So let's imagine now that this planet in front of our M dwarf is twice the size of the Earth. If we make the assumption that its atmosphere is still this sort of secondary outgassed atmosphere with a high mean molecular weight, you do get a slight boost in the size of the atmosphere, because the ring of atmosphere is larger around something which is twice the size of the Earth. However, we have a reason to think that the signal size would be proportionally larger. Let me argue why that would be. So this is showing a plot which is very common among folks interested in exoplanets, the mass of the planet along the x-axis and the planet's radius along the y-axis. Reassuringly, there's Earth, shown in a dark line at 1 times Earth radius, 1 times Earth mass. So I want to emphasize that in this part of parameter space, up to the radius of Neptune at 4 times the radius of the Earth, we have no solar system analog. So it was a complete mystery until roughly about 10 years ago. The work of Leslie Rogers at the University of Chicago showed that planets change from being more terrestrial in nature to being more sub-Neptunes with more of a hydrogen-helium atmosphere at about 1.5 times the radius of the Earth. So let's consider now our 2 Earth radius planet. It is likely not a bare rock. That's something we had to discover phenomenologically. There were theoretical models supporting both ideas prior to that time. So probably this 2 Earth radius planet has an extended atmosphere, perhaps having a little bit, a small fraction of water on top of it, in addition to at least some percentage of hydrogen. So now I've shown this more generous ring around the atmosphere, so lower mean molecular weight, fluffier atmosphere. All of a sudden, maybe 300 parts per million would be required to detect this atmosphere. So I showed that hypothetical James Webb spectrum a couple slides ago. This is a real James Webb spectrum, which we'll talk more about in detail this afternoon, and I want to emphasize that 300 parts per million. It is roughly the size of these features between the bottom part of this transmission spectrum and the top part. So you can see why exactly we designed James Webb to be as precise an instrument as it is. So in the time that I have remaining, I want to talk about one complication. So our understanding of planetary bodies, let me maybe return to this figure. To understand a planet in full is not only to detect the molecular content of its atmosphere, but also to understand its interior. These are relatively coarse measurements, but they are measurements. So understanding the extent to which something is made of pure MgSiO3, or perhaps some fraction of iron, like Earth. These are things that we can have at least some statistical arguments about when we talk about planets and actually putting them in context. But there's another mystery, so we're sort of abutting our knowledge in multiple fields. One of them is, what are planetary interiors made of? These things for which we have no solar system analog, presumably formed from material which is slightly different from which the host star is also formed. But one of the biggest challenges is actually not related to our understanding of planets at all. In fact, it's related to our understanding of stars. Now, we have our most familiar and friendly star, backlighting Titan, here. But other stars we can't observe in the same type of exquisite precision that we can actually resolve the surface of our own star and see whether it has spots on it. You've probably heard about or even seen star spots through welder's glass if you've ever looked at an eclipse, but it's actually the bright plages which might actually be a more present a greater difficulty with the understanding of exoplanets, both measuring their masses and seeing them in transit. This particular figure from Ben Rackham shows what's called the transit light source effect. What's concerning is that the exoplanet and its color-dependent, the color-dependent absorption of the atmosphere is not the only color-dependent feature, which is apparent on the surface of the star. Star spots are not like black individual objects. They are in fact cooler black bodies with their own complicated magnetic structure, so that I'm showing here an example on the left-hand side. Well, that's that delightful figure, which Sarah just argued should be so interesting for interpretation. You can see as a function of wavelength, the relative transit depth is changing. Yet this is not attributable to planets at all. I emphasize it's not related to the planet actually occulting the star spots. That's a different and important effect. This is unocculted star spots that putting the planet in front of the star, suddenly the light budget of what colors you're seeing can change dependent on the nature of those star spots and their colors and the fraction of the stellar surface that they cover. So at right here is probably the most worrying plot, I would say, from the talk I'm giving, which is showing like that relative transit size change. We're talking about a pinch, give or take. This is actually specific to the TRAPPIST-Emdorff system. Emdorffs are also particularly active, meaning this is especially pressing. So from stellar contamination alone, our ability to distinguish between the size of the planet at different wavelengths is really challenged by the presence of star spots. The size of the signal from the planets, in contrast, is shown with this sort of dotted gray. So you can see that one's ability to actually extract an understanding of the molecular content of atmospheres is intimately linked with our detailed understanding of stellar activity. You might ask, how is that going to be possible to overcome? There are ways to overcome it, but we are pressing up against our understanding of how to do that. This is from a NASA working group that posed the question in the following way: how do we translate knowledge of surface heterogeneities on other stars to transit observations? There's a couple ways in which to do it. One of them has to do with understanding our own star better. So I haven't talked at all about the means by which we actually extract mass measurements of stars, but one of the world-class instruments, the HARP spectrograph, the HARPS spectrograph, actually has a solar telescope appended to it, which feeds photons from our own sun into the same spectrograph that we use to observe exoplanetary host stars. We also have contemporaneous imaging from the SOHO Space Telescope to tell us if we're looking at a spectrum that is unresolved of some host star, how would we ever know what's going on in the surface? Well, with the sun, we actually can. That's one way of doing it. Also by actually observing solar system planets in transit, passing over surface inhomogeneities of our own sun, such as with the transit of Venus in 2012. Another way of doing this is what Rackham himself has really pioneered with the so-called transit light source effect, which is to observe the spectrum of the star and actually decompose it into its constituent spectra. Some fraction contributed by the stellar photosphere at one temperature, some other fraction in some linear combination contributed by the sum total of the spots. One would also have to make sure to model the star's rotation in and out of when the planet is appearing and when it's not, to sort of get a sense for what the star spot coverage is. There's a number of ways of starting to do this, yet I want to impress upon you the fact that this challenge is probably just as great as the technological challenges associated with the detection of planet atmospheres. So I hope that's an optimistic conclusion, but thank you very much for listening.